We have an objective for policy optimization. We also have the policy gradient theorem, which gives us a simple expression for the gradient of that objective. In this video, we'll complete the puzzle by showing how to estimate this gradient using the experience of an agent interacting with the environment. After watching this video, you will be able to derive a sample-based estimate for the gradient of the average reward objective. We want to derive a gradient ascent algorithm for our policy. We have our objective and its gradient due to the policy gradient theorem. Now we need to figure out how to approximate this gradient. In fact, what we will do is get a stochastic sample of the gradient. Recall this expression for the gradient of the average reward. Computing the sum over states is really impractical, but we can do the same thing we did when deriving our stochastic gradient descent rule for policy evaluation. We simply make updates from states we observe while following policy pi. This gradient from state st provides an approximation to the gradient of the average reward. As we discussed before for stochastic gradient descent, we can adjust the weights with this approximation and still guarantee we will reach a stationary point. This is what the stochastic gradient descent update looks like for the policy parameters. We could stop here, but let's simplify this further. Let's re-examine this from a perspective based on expectations. This will help us simplify the update and give you more insight into why the update makes sense. Notice that the sum over states weighted by mu can be rewritten as an expectation under mu. Recall that mu is the stationary distribution for pi, which reflects state visitation under pi. In fact, the states we observe while following pi are distributed according to mu. By computing the gradient from a state st, we get an unbiased estimate of this expectation. Thinking about our stochastic gradient as an unbiased estimate suggests one other simplification. Notice that inside the expectation, we have a sum over all actions. We want to make this term even simpler and get rid of the sum over all actions. If this was an expectation over actions, we could get a stochastic sample of this too, and so avoid summing over all actions. Here we're going to see how we can get an unbiased gradient estimate using only one action, AT, which is the action taken by the agent. It would be nice if the sum over actions was weighted by pi, and so was an expectation under pi. That way, we could sample it using the agent's action selection, which is distributed according to pi. It turns out this is an easy problem to solve. To get a weighted sum corresponding to an expectation, we can just multiply and divide by pi of a given s. Now we have an expectation over actions drawn from pi for this term. The new stochastic gradient ascent update now looks like this. As an aside, it is common to rewrite this gradient as the gradient of the natural logarithm of pi. This is based on a formula from calculus for the gradient of a logarithm. Using this rule, we get that the gradient of ln pi equals the gradient of pi over pi. So this update is equivalent to what we started with. But why do we do this? One reason is that it is actually simpler to compute the gradient of the logarithm of certain distributions. The other, less important reason is simply that it lets us write this gradient more compactly. In the end, it is just a mathematical trick, so don't let it distract you from the underlying algorithm. We now have something that looks like many of the learning rules used in this course. We adjust the parameters theta proportionally to a stochastic gradient of the objective. We use a step size parameter alpha to control the magnitude of the step in that direction. So alpha has the same role it always has. And that's it. We now have a nice clean update rule to learn the policy parameters. The last thing to talk about is how to actually compute the stochastic gradient for a given state and action. We just need two components, the gradient of the policy and an estimate of the differential values. The first is easy. We know the policy and its parameterization, and so can compute its gradient. The action value can be approximated in a variety of ways. For example, we could use a TD algorithm that learns differential action values. In an upcoming video, we will go through one particular choice in detail, as well as how to compute the gradient for specific policy parameterization. In this video, we derived a policy gradient learning rule for the average reward setting. In the next video, we will see how to use this rule.